Beneath the streets of Philadelphia, Boston, and New York, there are water pipes made of wood. Not iron, not clay. Wood. Hollowed-out tree trunks, bored end to end, joined with iron bands, and buried underground. Some laid in the 1700s, and some, 200 years later, still had water running through them when crews dug them up. Before iron foundries could produce pipe at scale, America had no choice. If a city needed water, someone had to find a straight log, bore out the center, and bury it, mile after mile. This is the story of how America's first cities solved an impossible problem with nothing but trees, hand tools, and the kind of stubborn ingenuity that built this country from the ground up. A story of crisis, desperation, and the anonymous workers who gave us something we now take completely for granted. To understand why anyone would attempt to move water through hollowed-out logs, you first have to understand what American cities looked like in the late 1700s. Philadelphia in 1790 was the largest city in America. Nearly 45,000 people packed into streets that had no sewers, no drainage, and no reliable water supply. If you wanted water, you had one of three options. You could dig a well in your backyard and hope the groundwater wasn't contaminated by your neighbor's privy pit. You could pay a water carrier to bring you buckets from the Delaware or Schuylkill rivers, or you could collect rainwater in barrels and pray it didn't run out during a dry summer. None of these options were good, and all of them were getting worse every single year as more people crowded into the city. The well situation was particularly grim. Colonial homes had no indoor plumbing, which meant every house needed an outhouse. These privies were essentially holes in the ground, sometimes lined with wood or brick, where human waste accumulated until someone hauled it away. The problem was that groundwater doesn't respect property lines. Dig a well 30 feet from a privy, and you might as well be drinking directly from the privy itself. The wealthy could afford to dig deeper wells, hire water carriers, or purchase filtered water from private vendors. The poor drank whatever they could get. That usually meant water that had passed through layers of contaminated soil, picking up waste from dozens of sources along the way. The taste was often tolerable. The bacteria were not. The problem wasn't just convenience, it was survival. Every summer brought yellow fever. But the epidemic of 1793 killed nearly 5,000 people in Philadelphia alone. That's 1 in every 10 residents. Bodies stacked in the streets. Entire neighborhoods abandoned. The wealthy fled to the countryside while the poor died where they lived, unable to escape, unable to afford the medicines that might have saved them. Dr. Benjamin Rush, one of the most prominent physicians in America, treated patients until he himself fell ill. He recorded what he witnessed with the clinical precision of a man trying to make sense of chaos. Victims developed fever, headache, pain in the back and limbs. Within days, their skin yellowed. Blood seeped from their gums, their noses, their eyes. They vomited black bile, a mixture of blood and stomach acid that gave the disease another name, the black vomit. As doctors at the time didn't understand that mosquitoes transmitted the disease. They blamed bad air, called miasma, rising from swamps and rotting matter. But they observed something important. The disease struck hardest in the poorest neighborhoods, the areas with the worst sanitation, the places where garbage rotted in the streets and the water in the wells tasted like decay. The connection wasn't perfect, but it was clear enough. Clean water might not cure yellow fever, but dirty water certainly wasn't helping. And even setting aside disease, the simple daily need for drinking water was becoming impossible to meet. By 1790, Philadelphia's population had grown faster than its water supply could handle. The dock creek that once provided clean water had become an open sewer. It was the springs that early settlers had relied upon were either depleted or contaminated. Water carriers charged premium prices that working families couldn't afford. Something had to change. But contaminated water wasn't the only crisis. Fire was the other. Colonial American cities were built almost entirely of wood. Houses, shops, warehouses, churches, all of it timber frame, all of it packed together on narrow streets, all of it ready to burn at the touch of a spark. The cooking fires never went out. Candles lit every room after dark. Blacksmith forges glowed red hot on every block. The entire city was essentially a pile of kindling waiting for ignition. And when fire broke out, there was almost nothing anyone could do about it. Fire brigades existed, but they were volunteer organizations with hand-operated pumps. These pumps, so-called hand tubs, were wooden boxes on wheels with piston-driven pumping mechanisms. 2 rows of men would work handles on either side, pushing up and down in alternating rhythm to force water through a hose. The pumps could throw water 30 or 40 feet, enough to reach the second floor of a typical building. But they had one fatal limitation. They required a constant supply of water to pump, and that water had to come from somewhere. Firefighters were limited by whatever water source happened to be nearby. If a fire broke out next to a well or cistern, they could fight it. If it broke out in a neighborhood with dry wells or empty cisterns, the firefighters could only watch it burn. Sometimes they pulled down adjacent buildings with hooks and chains to create fire breaks. Sometimes they formed bucket brigades, passing water hand to hand from distant sources. Sometimes they just stood there while entire blocks went up in flames. In 1752, a fire in Boston destroyed more than 100 buildings in a single night. New York had similar disasters. Philadelphia lived in constant fear that one spark, one knocked-over candle, one careless blacksmith could destroy decades of growth in a matter of hours. The fire of 1794 in Philadelphia proved just how vulnerable the city was. Starting near the waterfront, flames jumped from building to building along Water Street. Fire companies from across the city responded, but they couldn't get enough water to the pumps. The fire burned for hours, destroying properties valued at more than $500,000. In 1794 dollars, that was a staggering sum. Families lost everything. So businesses that had operated for generations vanished overnight. City leaders understood the problem. They needed water, not buckets of water, not barrels of water. A constant, pressurized supply that could reach every street and every neighborhood. The kind of supply that only a proper water system could provide. But here's the thing. In 1790s America, there was no such thing as a proper water system. The technology existed in theory. The Romans had built aqueducts 2,000 years earlier, carrying water across miles of countryside through precisely engineered channels. London had wooden water mains dating back to the 1600s. Chinese engineers had developed bamboo pipelines centuries before Europeans built their first aqueducts. But America had no infrastructure, no experienced engineers who had built such systems before, no manufacturing capacity to produce the components at scale, and most critically, no way to manufacture iron pipe at the quantities a city water system would require. Cast iron pipe wouldn't become commercially viable in the United States until the 1830s. American foundries in the 1790s could produce iron goods, but not in the lengths and quantities needed for miles of underground pipe. The technology simply wasn't there yet. That's 40 years away. Philadelphia couldn't wait 40 years. Boston couldn't wait. New York couldn't wait. People were dying now. Buildings were burning now. So the city councils faced a choice that seems almost absurd from our modern perspective. They could do nothing and watch their cities suffer through epidemic after epidemic, fire after fire, until something changed. Or they could build water systems out of the only material they had in abundance: trees. If you're enjoying this journey through America's forgotten engineering history, take a second to subscribe. Most of what built this country has been buried or forgotten. We're here to dig it back up. Now, building a water pipe out of a tree is not as simple as it sounds. You can't just take any log, drill a hole through it, and expect water to flow. The process began in the forest with the selection of the right timber. Not every tree makes a good pipe. The ideal log was straight, free of major knots, and between 8 and 12 inches in diameter. Larger logs were too heavy to transport and too difficult to work with hand tools. Smaller logs couldn't provide enough interior space for water flow once the center was bored out. Timber scouts would walk the forests around Philadelphia, marking trees that met the specifications. They looked for trunks that rose straight for at least 15 feet without significant branching or curvature. A log that curved even slightly would be impossible to bore straight through. The auger would exit the side, ruining the entire piece. The species mattered enormously. In Philadelphia and throughout the Mid-Atlantic region, workers favored American elm. Elm had several properties that made it almost perfect for underwater use. The wood was tough, resistant to splitting, and most importantly, it resisted rot when kept constantly submerged. This resistance to underwater rot seems counterintuitive. We think of water as the enemy of wood. Leave a wooden fence post in wet soil and it rots within a few years. Leave a wooden dock exposed to waves and it needs constant repair. How could a wooden pipe survive underground? The answer lies in the specific conditions of submersion. Wood rots because bacteria and fungi consume its cellulose fibers, but these microorganisms need oxygen to survive. When wood is completely submerged in water-saturated soil, oxygen cannot reach it. Without oxygen, the rot-causing organisms cannot function. The wood enters a state of preservation. A wooden pipe that alternated between wet and dry would decay within a few years. The cycles of saturation and drying create perfect conditions for fungal growth. But a pipe that stayed underwater, fully saturated, could last for decades. In some cases, centuries. Elm was particularly good at maintaining this saturated state. Its tight grain absorbed water slowly, but held it tenaciously. Once an elm pipe was buried in wet soil and filled with flowing water, it stayed wet. Other species were more porous. They would absorb water quickly, but release it just as fast during any interruption in service. Elm was stable, predictable, reliable. In New England, white pine was more common. Pine was softer and easier to bore, reducing the labor required and the wear on boring machines. But it didn't last as long as elm. Boston's wooden mains needed replacement more frequently than Philadelphia's. The trade-off was faster installation versus longer lifespan. New York used a mix of species depending on what was available from the surrounding forests. Long Island provided some timber, the Hudson Valley provided more. The key was finding logs that were straight enough to bore cleanly and dense enough to withstand the pressure of flowing water. Once a suitable log was selected, it had to be transported to the boring site. In the 1790s, this meant oxen, chains, and back-breaking labor. Logs weighing several hundred pounds were dragged along dirt roads, sometimes for miles, to reach the workshops where the boring machines waited. The roads themselves were barely worthy of the name. Unpaved tracks rutted by wagon wheels and churned to mud by rain, oxen strained against their yokes while teamsters shouted commands. A single log might require an entire day to transport, depending on the distance and terrain. Winter made transport easier in some ways. Frozen ground provided a harder surface for dragging. Snow could be packed into improvised sled tracks. But winter also brought its own hazards. Cold, stiffened ropes snapped under tension. Exhausted oxen collapsed and had to be replaced. Workers suffered frostbite on their hands and faces. The boring machine itself was a remarkable piece of engineering. Picture a massive wooden frame, perhaps 20 feet long, with a horizontal cradle that held the log in place. Iron clamps gripped the log at both ends, preventing it from rotating as the boring tool advanced. At one end of the frame sat the auger. This was a spiral cutting tool, similar in principle to the hand augers that carpenters use for small holes, but scaled up to industrial proportions. The cutting head was forged iron, shaped into a helical screw with sharpened edges. Behind the cutting head extended a long shaft that ran the length of the frame. At the other end of the frame, a team of horses or oxen walked in circles around a capstan. This was a vertical drum with horizontal arms extending outward. The animals pushed against these arms, walking round and round in an endless circle. Their circular motion was translated through gears and linkages into rotational force on the auger shaft. Slowly, inexorably, the spinning auger advanced into the end of the log. The auger had to be perfectly centered. If it wandered even slightly off course, it would exit the side of the log, ruining the entire piece. Experienced operators could tell by the sound whether the boring was proceeding correctly. A smooth, steady grinding meant the auger was tracking true. A stuttering, catching sound meant trouble. Boring a single log could take hours. The auger advanced slowly, cutting a 3 to 6 inch hole through 10, 12, and sometimes 15 feet of solid wood. Workers had to stop periodically to remove the wood chips that accumulated around the cutting head. They would withdraw the auger, clean out the chips, sharpen the cutting edges if necessary, and then resume. The smell was distinctive: fresh wood shavings, sap, and the metallic tang of the auger blade cutting through fiber. In summer, the scent of sawdust mingled with sweat and horse manure. In winter, the cold air carried the smell for hundreds of yards. You could find a boring operation by smell alone. The sound was a low, grinding hum as the tool bit through heartwood and sapwood alike. You could hear a boring machine working from a quarter-mile away. In the forests around Philadelphia, these sounds became familiar: the groan of oxen, the shout of teamsters, the endless grinding of iron through wood. Once the log was bored through, both ends had to be prepared for joining. This was where the real craftsmanship came in. The most common joining method used tapered ends. One end of each log was cut to form a slight point, perhaps 2 inches narrower than the main diameter. Think of a sharpened pencil, but in massive scale. The receiving end of the next log was reamed out slightly to accept this tapered end, creating a socket that the point would fit into. When the two were fitted together, the tapered end sat inside the ream section, creating a crude but effective seal. Wood swells when wet, so once the joint was buried and water began flowing, the wood would expand slightly, tightening the fit, but wood alone couldn't hold back water pressure. To reinforce the joints, workers wrapped iron bands around the connection points. These bands, forged by local blacksmiths, were heated until red hot, then hammered around the wooden joint. As the iron cooled, it contracted, squeezing the wooden ends together and creating a tighter seal. The process required precise timing. If the band was too hot, it would scorch the wood and weaken the joint. If it was too cold, it wouldn't contract enough to grip properly. Experienced blacksmiths developed a feel for the right temperature, judging by the color of the glowing metal. Cherry red was too hot. Dull red was about right. The bands had to be applied quickly before they cooled too much. Some systems used a different approach. Instead of tapered ends, workers drove iron collars over both ends of adjacent logs, binding them together like the rings on a barrel. These collars were split along one side, allowing them to be opened and fitted around the logs, then hammered closed. Others packed the joints with oakum, the same tarred rope fiber used to seal the seams of wooden ships. The oakum was driven into any gaps with caulking tools, then the iron bands were applied over the top. This provided a double seal, mechanical and chemical. None of these methods were perfect. Leaks were inevitable. But in a gravity-fed system, where the water pressure was relatively low, they were good enough. Water that leaked into the surrounding soil simply seeped away. The main flow continued toward its destination. If this is the kind of deep dive into forgotten American craftsmanship that you appreciate, hit subscribe. There's so much more buried under these streets. Philadelphia's water system, begun in 1799 and completed in 1801, was the first large-scale municipal water project in America. The man behind it was Benjamin Henry Latrobe, an English-born architect and engineer who would later become famous for his work on the United States Capitol building. Latrobe had studied engineering in Europe, where he'd seen both ancient Roman aqueducts and modern British water systems. He understood the principles involved. Water flows downhill. If you can lift it to a high point, gravity will carry it wherever you need it to go. The challenge in Philadelphia was getting the water up to that high point. Latrobe's plan was ambitious. He proposed drawing water from the Schuylkill River, pumping it up to an elevated reservoir using steam-powered engines, and then distributing it throughout the city using a network of underground mains. The distribution mains would be made of wood because there was no other viable option. The project required thousands of logs. Teams of workers fanned out across the surrounding countryside, selecting trees, felling them, and hauling them back to Philadelphia. The boring machines ran constantly, some of them operating 16 hours a day during the peak construction season. At the height of construction, multiple machines operated simultaneously, each one slowly grinding its way through log after log. The workforce was massive and anonymous. day laborers hired by the job, immigrants fresh off ships from Ireland and Germany, free black workers seeking any employment they could find. They appear in the records only as line items in expense ledgers. Labor for tree cutting, labor for transport, labor for boring, labor for trenching. We know their costs. We don't know their names. Latrobe faced constant challenges beyond just the labor. The boring machines broke down. Auger blades dulled and shattered against hidden knots in the wood. Logs that appeared sound on the outside turned out to be rotten at the core, discovered only after hours of boring had already been invested. Workers fell ill. Philadelphia's yellow fever returned in smaller outbreaks during the construction years. Men who reported for work one morning were dead within a week. Others simply didn't show up, having fled the city or succumbed to other diseases that thrived in the unsanitary conditions. Funding ran short repeatedly. The city council had allocated what seemed like a generous budget, but costs exceeded estimates at every turn. Latrobe had to plead for additional appropriations, explaining again and again why the project was costing more than planned. The council members grew skeptical. Some called for the project to be abandoned, but Latrobe persisted. He knew what Philadelphia was like without a water system. He'd seen the yellow fever victims. He'd watched buildings burn for lack of water to fight the flames. He understood what was at stake. The project took 2 years instead of the planned one. The original budget of $127,000 expanded to nearly $220,000 by completion. In $1,801, that was an enormous sum. Critics called it a boondoggle. Skeptics predicted failure. But in 1801, the system came online. Water from the Schuylkill River flowed through wooden pipes to a pumping station on Center Square, where 2 massive steam engines lifted it to an elevated reservoir. From the reservoir, the water descended through wooden mains into the streets of Philadelphia. For the first time in the city's history, residents could access clean river water from public hydrants throughout the city. No more hauling buckets from contaminated wells, no more paying water carriers who might bring water from God knows where. Clean water, available to anyone who walked to the nearest hydrant. The hydrants themselves were simple wooden posts with spigots, placed at intervals along the major streets. Residents gathered with buckets and barrels to collect their daily supply. Lines formed at popular hydrants, neighbors chatting while they waited their turn. For the poor especially, this was a revolution. Water that had been a scarce commodity was now free and abundant. But the real transformation wasn't convenience, it was fire protection. With pressurized water available at hydrants across the city, fire brigades no longer depended on wells and cisterns. When flames broke out, firefighters could connect their pumps to the nearest hydrant and draw water continuously. No more running dry in the middle of a fight, no more watching helplessly as fires spread beyond their reach. The Philadelphia water system didn't eliminate fires, but it made fighting them possible in ways that had never been possible before. Buildings that would have burned to the ground could now be saved. Fires that would have spread across entire blocks could now be contained. The days of watching helplessly while the city burned were over. The wooden water system that Philadelphia pioneered wasn't just a temporary solution. It worked, and it worked far better than anyone had a right to expect. Elm logs buried in water-saturated soil entered a state of preservation that bordered on the miraculous. The constant submersion prevented oxygen from reaching the wood. Without oxygen, the bacteria and fungi that cause decay couldn't survive. The logs essentially became pickled, preserved in the same wet environment that kept them functional. Maintenance crews learned to leave well enough alone. A wooden main that was performing well wasn't dug up for inspection. Digging exposed the wood to air, which started the clock on decay. As long as water flowed and pressure held, the pipes were left in place. When problems did occur, they usually happened at the joints. The iron bands could rust through. The wood at connection points could split. Tree roots sometimes found their way into the gaps, seeking the water inside. Sure repair crews would excavate the damaged section, cut out the bad joint, and splice in a new length of pipe. These repairs required the same boring and joining techniques used in original construction, a specialty trade developed around wooden pipe maintenance. These men knew how to find leaks by listening for the sound of rushing water through the soil. They would walk the streets at night when the city was quiet, pressing their ears to the ground, tracking the telltale whisper of escaping water. They knew which types of damage could be patched and which required full replacement. A single split joint could sometimes be rewrapped with new iron bands. A section of cracked pipe needed to be cut out entirely. The decisions required judgment that couldn't be taught from books. It came only from years of working with wood and water and soil. They carried the tools and skills of a technology that was already becoming obsolete. Because here's what's remarkable. Even as Philadelphia was completing its wooden water system, the technology to replace it was being developed. Cast iron foundries in England were already producing iron pipe for London's expanding water network. American foundries were catching up. Within 30 years, iron would be cheap enough and available enough to replace every wooden main in the country. But those wooden mains didn't simply disappear. And this is where the story becomes genuinely strange. When iron pipe became the standard in the 1830s and 1840s, cities faced a practical question. What do you do with thousands of wooden pipes buried beneath streets, buildings, and sidewalks? The answer, in most cases, was nothing. Digging up wooden mains was expensive and disruptive. The streets would have to be torn up. Traffic would be blocked. Businesses would complain. Residents would lose water service for days or weeks while the transition occurred. And for what? The old wooden pipes weren't hurting anyone. They were just sitting there, underground, filled with stagnant water or soil that had seeped in after they were disconnected. So the iron mains were laid alongside the wooden ones, or above them, or in entirely different trenches. The wooden pipes stayed where they were, entombed beneath layers of new construction, waiting. More than a century passed, then 2 centuries. Cities grew upward and outward. Streets were paved with cobblestones, then torn up and paved with brick, then torn up and paved with asphalt. Sewer lines were added, then gas lines, then electrical conduits, then telephone cables. Layer after layer of infrastructure accumulated underground. Nobody thought about the wooden pipes anymore. They had become part of the geological record, artifacts from an era that most people had completely forgotten. And then construction crews started finding them. In 1970, workers digging a foundation in downtown Philadelphia hit something unexpected. Their excavator struck wood, not rotten wood, solid, intact wood, shaped into a perfect cylinder with a hollow center. They had uncovered a section of the original 1801 water system. The logs were still there, still recognizable, still so well preserved that you could see the tool marks from the original boring machines. After 169 years underground, the elm wood had darkened to the color of chocolate, but it hadn't decayed. The iron bands at the joints were rusted and fragile, but the wood itself was sound. The workers stopped digging and called in experts. Historians and archaeologists arrived to document the find before construction resumed. They measured the pipe diameter, noted the joining method, took samples for analysis. They photographed the tool marks, evidence of the boring machines that had shaped this log more than a century and a half earlier. Similar discoveries have happened in Boston, New York, and smaller cities throughout the Northeast. In 2008, contractors in Boston found wooden pipes from a system installed in 1795. Some of these pipes still contained water. Not flowing water, but the stagnant remains of the last water that had passed through them before they were disconnected. In New York, sewer construction in Lower Manhattan has uncovered wooden mains from the Manhattan Company system, an early private water supplier that used hollow logs to distribute water before the Croton Aqueduct made civic water available. Archaeologists and historians have studied these discoveries carefully. The wooden pipes provide a physical record of early American engineering. They show the boring techniques, the joining methods, the sizes and species of wood that were used. They're time capsules from an era when American cities were still figuring out how to be cities. But there's something else in those pipes, something that makes the discoveries more than just archaeological curiosities. In some excavations, crews have found the remains of repairs that never quite worked, patches over patches. And makeshift solutions that someone applied in the 1820s or 1830s trying to squeeze a few more years out of infrastructure that was already obsolete. You can see the desperation in the work. The original craftsmanship was careful and deliberate. The boring was clean. The joints were properly formed. The iron bands were evenly spaced. Someone took pride in this work when it was new. The later repairs were rushed, improvised, done by workers who knew the whole system was living on borrowed time. Extra bands hammered on at odd angles. Sections of wood wedged into gaps, oakum packed thick enough to suggest multiple applications. Band-aids on band-aids. These weren't abstract engineering problems. Behind every repair was a neighborhood without water. Behind every failed joint was a fire that couldn't be fought. Behind every delay in the iron replacement was someone, somewhere, still depending on logs hollowed out by hand. The transition from wood to iron wasn't clean or fast. It happened block by block, sometimes pipe by pipe, over decades. During that transition, workers had to maintain two systems simultaneously. The old wooden mains couldn't be abandoned until the new iron ones were tested and proven. So maintenance crews kept the wooden pipes functional even as they knew the whole network was being replaced. Think about that job for a moment. You're repairing a pipe made of wood using techniques developed before you were born, knowing that every piece you fix will be abandoned within a few years. The work requires just as much skill as it ever did. The consequences of failure are just as serious, but there's no future in it. You're the last generation of a trade that's already dead. That's the story of American infrastructure in a nutshell. The people who build and maintain the systems that make cities work are almost always invisible. We see the results of their labor every time we turn on a tap or flush a toilet or watch firefighters connect to a hydrant. But we don't see them. We don't know their names. We don't think about the fact that everything we take for granted required someone at some point to get their hands dirty. If you've stayed this long, you understand that history isn't just about famous names and grand events. It's about the workers who actually built the world. Subscribe if you want more of this. The wooden water pipes beneath Philadelphia aren't just engineering artifacts. They're monuments to the workers who bored them, joined them, buried them, and maintained them. Men whose names appear in no history books. Men who solved an impossible problem with nothing but trees and iron and the willingness to try. When we talk about the founding of American cities, we usually talk about politicians and architects. We talk about the grand plans and the famous names. Benjamin Franklin appears in every story about Philadelphia. George Washington gets credit for establishing the federal government there. But the real founders were the workers in the forests, selecting logs. The workers at the boring machines, guiding augers through solid wood. The workers in the trenches, fitting joints and wrapping iron bands. Without them, there were no cities, just settlements waiting to burn or die of thirst. The last wooden water main in active service in an American city was finally replaced sometime in the 1940s. By that point, the pipe had been underground for nearly a century and a half. It had outlasted the workers who installed it, the children of those workers, and their grandchildren. It had survived 2 world wars, the Great Depression, and technological changes that its original builders couldn't have imagined. And when crews finally dug it up, the wood was still sound. That's the paradox of the wooden water pipes. They were a temporary solution, a stopgap measure until something better came along. Nobody who installed them expected them to last. They were supposed to buy time, maybe 10 or 20 years, until iron foundries could catch up with demand. Instead, they lasted long enough to become archaeology, long enough to surprise the workers who eventually uncovered them. Long enough to prove that sometimes the temporary solutions we improvise in desperation turn out to be more durable than anything we plan. The story of wooden water pipes is really 2 stories. The first is a story about technology and innovation. American cities faced a crisis, and their engineers responded with creativity and determination. They took the materials available, logs and iron bands, and hand-powered boring machines, and they built infrastructure that worked. When better materials became available, they upgraded. The whole process took about 40 years, from the first wooden mains in the 1790s to widespread adoption of iron in the 1830s and 1840s. In the grand sweep of history, that's remarkably fast. But the second story is about labor and sacrifice. and every log that went underground represented hours of work. The men who felled the trees with axes and crosscut saws. The men who transported them over rutted roads with teams of oxen. The men who operated the boring machines through summer heat and winter cold. The men who dug the trenches by hand, moving cubic yards of soil with nothing but shovels and strong backs. The men who laid the pipes, fitted the joints, wrapped the bands, and filled the trenches back in. We don't have their names. The records from that era were kept by administrators and property owners, not workers. The men who actually built the system appear only as costs in accounting ledgers. Labor for boring, $12. Labor for trenching, $8. Labor for transport, $15. Numbers, not people. But we can imagine what their days looked like. Waking before dawn to the sound of roosters, walking to the work site through unpaved streets that turned to mud in rain and dust in dry weather, spending 8 or 10 or 12 hours at the boring machine, breathing sawdust that coated their lungs, muscles aching from the repetitive motion of feeding logs and clearing chips, drinking water from the same contaminated sources they were working to replace because the new system wasn't finished yet. Going home to families crowded into small houses in neighborhoods where the yellow fever struck hardest, knowing that tomorrow would be exactly the same, and the day after that, and the day after that. The yellow fever outbreaks didn't pause for construction projects. Workers got sick, some of them died, others took their places, the boring machines kept turning. This was the reality of building America, not grand visions and inspirational speeches, but grinding, dangerous, unglamorous work performed by people who had no choice. The wealthy citizens who would eventually drink clean water from the new system didn't dig any trenches. The politicians who took credit for the projects didn't bore any logs. The work fell to the poor, the immigrant, the desperate, and the work got done. That's what matters. Against odds that should have been impossible, with tools that were barely adequate, the work got done. 200 years later, we walk over these pipes without knowing they're there. We turn on taps and assume that water will flow. We don't think about the centuries of labor and innovation that made indoor plumbing possible. We don't think about the workers who died to give us something we take completely for granted. But the pipes remember. Somewhere beneath the streets of Philadelphia, Boston, and New York, there are still sections of wooden main that have never been found, still buried, still intact, waiting for some future excavation to bring them back to light. When that happens, someone will look at the darkened wood and the rusted iron bands and wonder who made this, who bored this log, who wrapped this joint, who laid this pipe in the ground and walked away, not knowing that their work would outlast everything else they ever did. We don't have their names, but we have their work. And in the end, that's how most of us are remembered. Not by what we said or what we owned, but by what we built and what we left behind. The wooden water pipes beneath America's oldest cities are monuments to forgotten workers. They're proof that ordinary people, using ordinary materials, can create things that last far beyond their own lifetimes. They're reminders that every convenience we enjoy was paid for by someone else's sweat and blood. The next time you turn on a tap, think about the tree that might have carried that water 2 centuries ago. Think about the men who hollowed it out, joined it to its neighbors, and buried it in the earth. Think about the faith it took to believe that this strange, improvised system would actually work. It did work. It worked so well that we forgot it was ever there. That's the highest compliment you can pay to infrastructure. When it becomes invisible, that means it succeeded. But invisible doesn't mean insignificant. The wooden water pipes mattered. The workers who built them mattered. The story of how American cities solved their first great infrastructure crisis matters. Because we're still solving those crises. We're still building systems that we hope will outlast us. We're still depending on workers whose names we'll never know to keep those systems running. The materials have changed, the techniques have evolved, but the fundamental challenge remains the same. How do you bring essential resources to the people who need them? How do you protect cities from fire and disease? How do you build something that will last? The workers who bored logs in the 1790s found answers to those questions using nothing but trees and iron and human determination. Their answers lasted 200 years. What will our answers leave behind? Somewhere beneath your feet, if you live in one of America's oldest cities, there might be a wooden pipe that still remembers. The wood has darkened, the iron has rusted, the water stopped flowing long ago, but the pipe is still there, still waiting. Still proof that when American cities faced an impossible problem, the workers of this country found a way. They built a water system out of trees, and it worked. That's the legacy of the wooden water pipes, not just an engineering curiosity, not just an archaeological artifact. A testament to what ordinary people can accomplish when failure isn't an option. That's America.